Today I'm going to talk about the Runtime Library. The Runtime Library is part of Mathematica, and it's part of the new compiler. It's part of the old compiler. It's essentially a core shared component for numerical computation. Its focus is on machine arithmetic, fast machine arithmetic. Today I'm going to describe the design and new work to improve it. And when I describe the new performance enhancements, so even if you just use Mathematica as a casual user, nothing to do with the compiler, you will see some benefits from using it in the next version. But of course, the benefits will be more significant if you use it through the new compiler infrastructure. So, as I said, the Wolfram RTL is, here it is, sitting in the middle here. It services the kernel when the kernel does machine arithmetic. It services the new compiler and the old compiler. It also supports when standalone code is generated. It supports the functions generated in the standalone code. It also supports library link, functionality library link. And for the future, I'm told that there's interest from very high up in the front-end group to start using Wolfram RTL in the future. So what happens in the kernel has interpreted code. At some point, that interpreted code needs to do some machine arithmetic or packed array computation, and then that's passed over to the Wolfram Runtime Library where the actual computation is done. So it's the home of where. Yeah, so here's a little graphic that I took from Abdul's talk here. So this is like a schematic of the new compiler with the type analysis, the abstract syntax tree, instruction registers, and Wolfram RTL is down here when the code generation and the actual computation starts to happen. So the Runtime Library provides core data structures and operations for the kernel and the compiler. M-tensor, which is the heart of the packed array, the sparse array, machine sparse array computation, and new in this version is the numeric array. If anybody went to Piotr's talk, you would have seen that. Generalization of packed arrays to an extended set of types, 8-bit, 16-bit machine integers, floats, etc. It provides machine arithmetic for scalar and vector operations, core linear algebra operations, dense and sparse blars, random number generation, has hash functions, hash tables that are used in the kernel. It has a fast thread-safe memory allocator that's built. It also provides a threading layer, which will then abstract away to a system-specific, platform-specific thread like pthreads on Linux or something. So more recently, we've added support for many, many more types in order to be able to support numeric array and in order to be able to compile to different types in the new compiler. So 8, 16, 32, 64-bit signed and unsigned integers, 62, 64, and 32-bit floats, which are native, and we use a little library available for all platforms to be able to perform arithmetic with 16-bit floats, which are generally only available on GPUs, but we want to provide that functionality even on a CPU. So you could develop your code using a smaller floating point footprint and then go and take it over to a GPU. And also a lot of new support functions for the new compiler. So the design, it's standard compliant, so we use a C++ specific standard. It has platform-specific optimizations like compiler intrinsic functions, and it uses special-purpose arithmetic-oriented libraries like Intel's MKL or IPP. The objectives of the Mathematica compiler would be to generate more efficient compiled code, to extend Mathematica using the new compiler instead of having to write stuff in the kernel, and then also to provide the user with some sort of code that runs just as efficiently as something that would be built into the kernel. So those are the objectives. So here's an example, interpreted computation done through Mathematica and through the evaluator. So we'll just take the maximum machine integer on this machine, 2 to the 63 minus 1, signed integer. We'll add 1 to it. This is then interpreted. Mathematica goes down to its plus function. The plus function calls the runtime library. The runtime library says, this is too big to fit into a signed machine integer, and it returns an error code back. So the kernel plus function then says, oh dear, I better go and redo that computation, and the computation is returned as a big integer. So that error's trapped, and then the kernel will go and use its extended set of types to be able to go and carry on the computation. And so the result is no longer a machine integer. But inside, as an intermediary set, there's been a call out to the runtime library, and it's been able to determine that the result couldn't be done using machine integers. Similar sort of thing with packed arrays of floating point numbers. So here I've made a small packed array, and I've set the last entry to be the maximum machine number. It's a packed array. You can take the square root of this packed array, and this is done using vectorized arithmetic then. But if I square that packed array, then this number is too big to be represented as an IEEE floating point number. So what happens is the runtime library does the computation, finds that there's been a floating point overflow error, returns that back to the kernel, and then the kernel will go and take some course of action, unpack the packed array, and then go and do the evaluation using its own expression arithmetic. So the result is then an arbitrary precision floating point number. So we've re-implemented the runtime library. The previous versions were written in C. Now it's written in C++. Not all of the code has been converted yet. I'd say about half of it, something like that. Some of the things that we wanted from C++, templates, obviously we have an extended set of types, many new types, and the template mechanism of C++ was quite important. Also, operator and function overloading was quite important. The fact that you can use classes to reorganize work was very important. This is becoming quite a big project now, and we want a better kind of organizational infrastructure. C++ provides that. Performance, well, what I mean by performance is C++ has this ability to do more work at compile time and less work at runtime. So if you set things up properly, you can push work into the compiler. So it takes longer to actually, for us, to build and compile the runtime library, but then the user who uses the library actually has code that executes more quickly. Another thing that we found useful, and this is very project-specific, is the fact that you can use exceptions in C++. So in our old C interface, we would pass around flags to say there's been an error propagated. Then you need to go and check that flag. If there's a flag, return an error flag. Okay? And that's very, apart from the fact that you're paying the price of adding if statements everywhere, it's very error-prone. You forget to put it in one place, and that exception is not caught and not returned to the kernel. So we use C++ exceptions now. If there's no exception occurred, you pay no penalty. There's no longer a test of an if statement of a flag for every single function. So the code runs more efficiently. So here's an example in the new compiler. You've seen this already. Here's a function with a typed markup, and it's just adding two 64-bit integers together. And then I'm going to compile this using the new compiler, and it looks like this in two stages. So the first thing it does is generate this system plus interface layer, and then this system plus interface layer calls here down into the runtime library where the actual arithmetic is performed. And then later, in some later compiler pass, this might be inlined back into here, and we're only left with the call out to the runtime library that actually does this plus operation. So another thing we've been working on is, as we overhaul the code, we're not just converting it to C++, we're also trying to incorporate algorithmic improvements. So here's one example, integer powers. So in the new version of Mathematica, if you compute 3 to the power of 39, that's about 50 to 60% faster. So that's achieved in two ways. One is to use an optimized loop unrolled code. I'll explain a little bit that in the examples. And another is an algorithmic improvement that I'll also explain. So the first thing is when you compute integer powers, you don't compute them as successive multiplications. X to the 15 would need 14 multiplications. You do it with what's called binary exponentiation. So you go through the binary representation of 15, and depending on if it's a 1 or a 0, you square. And if there's a 1 present, you also do a multiplication. So this is like an SSA form, singular static assignment that's used inside the compiler. So you compute x squared, then x cubed, then x to the 6, then x to the 7, x to the 14, and finally x to the 15. Okay, so it costs 3 squarings, 3 multiplications, that's 6 products. Then if you want to compute a larger power, You take up where you left off, you do another squaring, another multiplication, another squaring, another multiplication. Finally, you get x to the 63, which is 10 products. So it looks like this. These are the powers that I want to compute, and as I go further down the tree, I need an extra multiplication each time I go down. Another thing you'll notice that when I compute x to the 39 here, it's actually more expensive than computing x to the 40, even though 40 is larger than 39. So what we did was build in what's called an addition chain exponentiation. So addition chains are sequences of index pairs such that each term is the sum of two previous terms. So it turns out that binary exponentiation is not optimal. In some certain cases, you can get an integer explanation more efficiently. So the first power at which this occurs is x to the 15. So here's an example. We square, multiply, square like before, but now we compute, instead of computing x to the 7, we compute x to the 12, and we compute x to the 15 as x to the 12 times x to the 3. So this is now only 5 products, and we saved 1 product. And a similar kind of thing for x to the 63. X to the 63 is the first power at which you can actually save 2 products compared to the binary exponentiation. So here's the tree for the addition chain, and you'll see it's a lot shallower and a lot more dense around here. Okay, that's an indication that there's some work being saved. So another thing that we really had to do was to break some kind of backward compatibility. So this is what happened in version 11.3. There haven't been too many users' complaints, but there was a fair amount of work inside the company. So hopefully those of you in the audience who did put work, Eduardo, Gosha, people who did put work into doing this, I'm hopefully going to convince you it was all worth it. So the whole point of this is that machine underflow is holding us back from doing very efficient vectorized machine arithmetic computation. So in version 11.3, we now just issue a message, but we allow the machine underflow to occur instead of going and switching to a very small big num. This allows fast vector arithmetic. It allows us to use much larger set of algorithms and libraries. And I'll show you a couple of examples. So first of all, before I go and show you the examples, let me explain a bit about how the vector arithmetic works in parallel. Say I want to compute a long vector and some operation on that long vector, plus, times, power, whatever. Say I have something with 64 blocks of data. If I split that up into blocks of 8, and I've got an 8-core machine, in an ideal world, if I ignore like overhead for scheduling and communication, et cetera, each core would be able to do 8 blocks of this computation, and I should get a speed up of about a factor of 8 in an ideal world. But in the real world, here, these red blocks are the CPU is busy doing something. Okay, it might be a web browser, it might be something else, it might be rendering, it might be something. So what the kernel does, or what the runtime library does, is it uses a different kind of scheduling where it sets up a block of 64, and each core, when it can, it goes and steals a block off this work list and then does this computation. And that means that we can, even when some cores are idle, we can go and get work from those cores and use them on another core. And so this core is doing like more than 8 blocks of work, and this one is doing only 2 because it was busy doing other things. But we still get some reasonably good speed up. Not the factor of 8 that was the ideal, but something that's close enough to it. So the other thing that we've done with the new runtime library is use a different parallelization strategy. So in previous versions of Mathematica, we used threading layer, pthreads on Linux or whatever. This is nice. It's a very powerful framework. It's quite complicated and difficult to extend. If I want to switch strategies for the parallelization, it's a lot of code and a lot of work to try and develop that. And it's quite heavyweight. It's a very, very high latency for very simple tasks. So the new runtime library uses OpenMP. OpenMP is a much more lightweight kind of threading layer. It's tailored towards fast numerical computation. And it's much more ideal for parallelizing vectorized operations, for example. So it's got a very low latency. It's reasonably flexible. It's got a variety of built-in schedulers that have been developed by people. And there's research work on doing things like work stealing, but work stealing from a nearby processor that has good cache coherency, for example. Things that will be much more difficult for us to develop. The other things, because it's an open program, you can also kind of tailor it for your machine. You can use environment variables to say, really give Mathematica priority in my threads over any other job that's running, something like that. So here are some examples. I'm going to use a 20-core machine. It's two-package Intel Xeon from about 2014, not state-of-the-art, but a reasonably nice machine. The cache, level 1 cache is 32K, level 2 cache is 256K, and level 3 cache is 2.56 megabytes. In previous versions of Mathematica, we would try to ensure that blocks would fit in level 3 cache. Now using OMP, we can use a smaller block size, and so you'll see a lot of the speed up comes from being able to work around the faster cache levels. You'll also see that the thresholds for the OMP code are lower, and some speed ups for shorter lengths. I should point out that all of these examples are worst case examples. So they're really the hardest things to parallelize. I'm talking about plus, times, minus, subtract. These are the functions that really show the highest overhead of communication in the threads. So here's machine integer speed up. So in blue is the old code for threading, and in orange is the new OpenMP code. So you see around 8,000 in length. The new OMP code starts to work in parallel, and this is version 11.3. So this is the serial speed up, so we can get very close to the actual 20 cores that we're using on the machine. And this is the actual execution time. You see the OMP starts to be able to parallelize for quite short lengths, and then it just keeps using more and more cores, so the execution time stays relatively constant. And then when it's got up to using all 20 cores, then the execution time increases. When we get to the very end here, there's hardly any speed up, and that's because we're essentially spending all our time fetching data from RAM. We're no longer living in the cache. And so when you get to very, very large lengths, the effects of parallelization are lost. So it's only in this kind of length that you can get any speed up. So about a factor of 5 for abs and minus, about a factor of 5 for integer plus, subtract, and times in the best case. The other thing that we did was to rewrite the way that vector operations work for so-called reduction operations. So a reduction operation is when you take a vector, you do some operation, and you get a scalar result. So an example of that might be the maximum value. Okay? The maximum value operating on a vector returns a scalar result. Or total. Total will go and sum through the entries but return a single entry as a result. So it's taking a vector space and returning a scalar operation. So what we did with the new implementation was we've re-implemented it to use to avoid thread contention. When it's going and working on this, computing this maximum value, or when it's going and working to compute these sums in total, each thread can now accumulate its own partial result without having to worry about what's going on in the other threads. And only when all the threads are done, it combines the results together. Before, each block at each step would have to recombine the results, and there would be kind of locking going on, causing sort of thread contention. So this is the result of maximum, and this is the result of total. You see you get about a 20% speed up, a 20-fold speed up, excuse me. And even the serial computation here is about twice as fast. This is the result of real and complex arithmetic. So here again, we get about a 10-fold speed up on the average, say 2 or 3 times faster. And the last thing that we're able to do now that we don't have restrictions of machine underflow is that we can use the faster arithmetic libraries to compute complex elementary functions. So one is the absolute value. This is now done through MKL. And this is the exponential function. And what you see here is, so there are two things going on here. One is that we're using MKL instead of C code, and that accounts for this region here, this factor of 3 or 4 speed up. And then the other one is the fact that we're using OpenMP instead of the threading that gives the additional boost here. So the short-term plans to continue the development of the runtime library. Well, the next thing to do is arithmetic on numeric arrays. So Piotr talked about the actual numeric array data structure. The data structure is there. You can read it out, write it out, represent it. We want to actually allow users to be able to operate and work on them, and we want to allow them to be used in the new compiler as a representation to do things with. Another one is to do single instruction, multiple data optimization. So I was talking about a parallel speed up in the range, say, 10,000 to 1 million. But all of the arithmetic from, say, 1 to 10,000, that's the range that we want to speed up now, short vector computations. And the way to do that is to try and block together operations and push them through the CPU pipeline, say 4 at a time, something like that, depending on what instructions are available on CPU. Another thing we want to look at is parallel directives, both inside the Wolfram Runtime Library and in the new compiler. We also need to generalize the linear algebra, particularly for, say, numeric arrays. We want to allow to be able to call BLAS and a linear solve or whatever with floating point arrays or matrices. Another thing that we'd like to do is move up to a slightly newer C++ standard that has functions. For example, in Tom's talk, he had an example of sorting. So there's functionality that can speed up sort of merge sort and other kinds of operations. And there are also a number of special functions implemented in the new C++ standard that we can make use of. Then we need to reorganize the Wolfram RTL as a dynamic library because there's interest, not just what we want to share it between the kernel and the new compiler, but also think about using it in other parts, like the front end. So some other things. So we broke arithmetic with this underflow. That was quite a substantial change with a lot of impact. We're thinking about some more minor things. So don't have a heart attack, those of you who worked on that. These will be much. I'm talking about point fixes. So in the old days, the focus of mathematics was on mathematics. Okay, so it would say the arctangent of 0 is indeterminate. But IEEE arithmetic says it's an exceptional case. Doesn't really matter what value you choose. We're going to choose the value 0. Okay, so the fact that this one value across the whole of arctan is different from Mathematica prevents us from using faster floating point arithmetic libraries. So what I've been doing is going through the elementary functions and cataloging these exceptional values. And what we'll try to do is move towards, at least for machine arithmetic, I'm only talking about, if you want to do symbolic calculations, arctan of an exact 0 will still be indeterminate, as it, you want the mathematical definition. But when you do floating point computations, you want something that matches the floating point standard. So that's a bunch of things that we're looking to change in order to try to make computations go faster and faster. Another thing might be to add representations of the IEEE infinity and nan, and then you could, say, not switch to arbitrary precision arithmetic. You could just, say, in a plot, you'll get an IEEE infinity back, but you'll get it back quickly, and you'll just prune it out. And you won't pay the cost of having to do the computation in arbitrary precision. Everything will be done purely in machine precision. That might also be something that the front end might be interested in. And also some other sort of minor changes to type consistency. So again, it's a kind of a mathematical decision. In Mathematica, when you take the imaginary value of 2.3, you get an exact 0. Okay, but really it should be a floating point 0 because it should be type consistent. The input type is a floating point number. The output type should be a floating point number. So in conclusion, we're developing the runtime library. We're trying to make it robust, efficient, type extensible for the new compiler to support an extended set of types. The incremental improvements that we're building into the runtime library aren't necessarily tied to the new compiler. So, for example, these improvements in this talk are all in the next release. We're trying to provide a compact, highly optimized core computational base. And then from that core computational base, people who want functionality that's not in the Wolfram runtime library will use the new compiler. And then the new compiler will use the core functionality in the runtime library, and then you'll be able to extend based on that through the new compiler. And the last thing is, it's really pushing the boundaries and quite an extensive stress test of compilers and third-party libraries. We found a number of bugs. I've been communicating with Intel. We found a number of bugs in MKL and IPP error handling. We create standalone examples. We send them off to the developers, which then get subsequently fixed. We found a number of bugs in Microsoft Visual Studio. Complex exponential error handling has been broken. We found 3 or 4 separate bugs, sent them off to the developers, and they've been subsequently fixed. We found a number of bugs in GCC, Clang, LLVM, and various of us communicate with developers of these external compilers and libraries to resolve these issues so that we can move forward. So I hope that's given you like an overview, and I hope that you found it useful. Thank you very much.